Thank you. I would have preferred a cool intro video narrated by Hugh Jackman like the keynote speakers, but that will do as well. So good afternoon, good morning. I'm still extremely jet lagged. I've completely lost all sense of time. But thank you for being here. Thank you for choosing to attend this presentation instead of some of the others. You've probably made a horrible decision, but you're here now, so we might as well continue. So before I start, I'll just like to introduce myself again. I'm from the SKA project, Omer Mahgoub, and I've actually never presented this topic to anyone before. I've never given a presentation on this. This is my first time doing it. And you might be wondering why I've decided to do this, especially here at the inaugural Altium event. So firstly, it's because I'd like to share with you about this exciting project and the amazing work being done on it, and of course, Altium's involvement in making that a reality. And secondly, and most importantly, because I wanted a free trip to San Diego. So ever since I've arrived here, I've been told by a lot of people, so I'm hoping you'll be able to understand me, because I've been told by a lot of people that I speak differently, that I say certain words differently, unlike the rest of you. And it's true, I might say some words differently, but that's mostly because I pronounce them correctly. So I'd just like to get started with this. And just as he mentioned, I'm an engineer. I'm not an astronomer. I'm not a physicist. So all of this is going to be at a very basic level. It's not going to be too high-tech. We're not going to get too involved in any of that. So what is the SKA? So first off, I'd like to start by telling you about the SKA in terms of the organization. It's a global non-profit organization that's headquartered in Manchester in the United Kingdom, and it consists of 10 member countries: Australia, Canada, China, Germany, India, Italy, New Zealand, South Africa, Sweden, the Netherlands, and Great Britain. I'm pretty good with my flags. As well as 8 African partner countries, which I'm not going to name because I'm not that great with my flags. But actually it's Botswana, Ghana, Kenya, Madagascar, Mauritius, Mozambique, Namibia, and Zambia. So the African partner countries are where the telescope will also be hosted, but they're not directly involved with the development of the telescope. So what are they doing? So they're building the Square Kilometre Array, which in essence is a radio telescope that is a mega science project. So in essence, it's on the same scale as projects like the Large Hadron Collider, and it's an effort to build the world's largest radio telescope, which in total will comprise a collecting area of 1 square kilometer. Okay, this was not supposed to be here. I thought I had removed this. But since it is here, you're going to have to see it anyway. So why is the USA not a member country of the Square Kilometre Array? No. I'm not even going to say it out loud. Okay, so how are they doing this? Now, a lot of people are not familiar with the concept of a radio telescope, but they might be more familiar with the concept of an optical telescope. You've all probably seen optical telescopes. A lot of people will have them at home. You know, you'll have it on your balcony. You'll use it to observe the neighbors across the road. You might use it to observe the stars, whatever you prefer. No judgments here. At planetariums, observatories. And so optical telescopes are used to observe visible wavelengths of light that we can see by the human eye. Whereas a radio telescope is used to detect radio waves emitted by celestial objects and objects in space, because most objects emit radio waves. And the advantage of radio telescopes, or rather not an advantage, but the difference, I mean, optical and radio have their own uses, but the one advantage that radio has over optical is that radio waves aren't hampered by clouds or poor weather conditions, that the wave will still be able to reach us on Earth. So over here, I have 2 images. The top is the sky as seen via the optical wavelength, and at the bottom is the sky seen at the radio wavelength of 1,420 megahertz. That's known as the neutral hydrogen emission line. Now, hydrogen is very important in radio astronomy because most of the galaxy, most of the stars and the planets are comprised of hydrogen. It's the most abundant element on Earth. So that's the sky seen in the 1,420 megahertz hydrogen line. And over here, we have another one of the sky seen in the 408 megahertz line. And now just to mention that, of course, this is all false color. This is not what is actually seen. It's actually data that is then interpreted by a computer to create sort of from blue to red, you're going from cool to hot, and that's the intensity. So wherever you see red, that's a high emissions, blue are cooler emissions. So these are essentially the different kind of views you will get from an optical telescope and from a radio telescope. So there are different types of radio telescopes. You get single dish telescopes. For example, this one here. I don't know if any of you have seen this or are familiar with this. No. Unfortunately not. This is the Arecibo Observatory. It's the Arecibo Observatory in Puerto Rico. It's 305 meters wide, and it was recently damaged by Hurricane Maria, but it's still slightly functional. Not too much damage has been done. And you might have noticed this because it was used in the film Contact, starring Jodie Foster. If you ever watch that movie again, you might notice this. You might also have seen it in GoldenEye, Pierce Brosnan. It was also located here. So this is a 305-meter dish. And then the one that you mentioned in China, oh, okay, we'll get to that one. Another thing that this is famous for is the Arecibo message. I don't know if many of you are familiar with the Arecibo message, but the Arecibo message was a message sent in 1974. This is the decoded message. So the message was encoded by Frank Drake and Carl Sagan. So I'm not even nearly intelligent enough to tell you how it was encoded. But that message was encoded and transmitted to a galaxy approximately 25,000 light years away. And the message contains certain information about humanity and about our planet, information like the numbers 1 to 10, the atomic numbers of all the elements that make up DNA, the formulas of the sugars and bases in DNA, the number of the nucleotides in DNA, and then a graphic figure here of a human being, the dimension of average man and the human population, as well a graphic of the solar system and the planet the message is coming from. And at the bottom, this is a graphic of the radio telescope itself. So this was transmitted in 1974. And considering that it will take 25,000 years to arrive to where it was being sent, 25,000 years for the message to be deciphered and returned to Earth, and also the fact that the galaxy to which it's being sent would have moved by the time that the message would have arrived, it was never really being sent with the hope of receiving a reply. This is sort of it's the intergalactic equivalent of sending a text to your ex. So the main reason that this message was sent was it was sort of to highlight mankind's innovation and technical achievement. It's sort of like a pat on our backs, just to remind ourselves of how amazing we are, considering that this was done in 1974. And if this was to have been sent today, it would probably look a little bit different. I imagine it would look something like this. We probably still wouldn't get a reply. We'd be on 2 gray ticks. And this is another example, though. This is the one in China. This is called the FAST telescope. FAST stands for 500-meter aperture spherical telescope. And this is currently the world's largest single-dish radio telescope. And as you can see, it looks very similar to the Arecibo Observatory because these kind of dishes are always tried to be positioned in areas that are quite high with very weak or very low radio signals and interference. This one is built up, I'm not sure if you can notice it, but a whole lot of different antennas that can actually move. So all of those antennas are able to move. At the moment, it's not really functional. I mean, it was commissioned in late September 2016, but I don't think it's really being used at the moment. Okay, so those were single-dish telescopes. Now, the SKA is not going to be a single-dish telescope. The SKA is going to be what's referred to as interferometry, or a radio telescope array. So what a radio telescope array does is that it links different telescopes in different parts or different areas, and together they're effectively used as one large telescope. So for example, this is the very long baseline array in the United States, and it consists of about, I think it's 10 dishes spanning all the way from Hawaii to the Virgin Islands. There are many more examples, especially here in the US. There's also this one here, which is called the Very Large Array. It consists of 27 telescopes. Each one is about 25 meters wide, and this is in Socorro County in the USA. This is a centimeter wavelength dish, so that means it picks up frequencies between 74 megahertz and 5 gigahertz, and 50 gigahertz, sorry. This is a very large baseline array. Over here, this is one of my favorites. I don't know if this image is real or Photoshop, but it looks really beautiful. This is the Atacama Large Millimeter Array, or the ALMA telescope. This is in the Atacama Desert in Chile. And this one here, it has 66 12-meter dishes, and picking up between 31 to 100 gigahertz. And I know it sounds like a bit of an oxymoron, a large millimeter, but whenever they speak about millimeter arrays, that's just the wavelengths that are of interest. Okay, so why are they doing this? Because you probably think there are already so many telescopes out there. Do we need to be spending more money on more projects that are unnecessary? And the answer is that there's still a lot that has been unexplored that current radio telescopes aren't able to provide us information about. There's a lot that we haven't seen yet. Sorry, excuse this. There's a lot that we'll get to that. There's a lot that we don't know yet about the world, about how it was formed, about how stars and galaxies form and evolve, about the Big Bang, if that's what you believe. If not, we're not here for that discussion. So there's a lot that we want to learn about how galaxies form and evolve, because they are constantly forming, constantly evolving, and we do not have enough answers about that. Also about cosmic magnetism. So magnetism is crucial to mankind. I mean, magnetism is what helps bees and birds navigate, as well as humans. Compass needles rely on magnetism. And there's a lot of magnetisms also exhibited by celestial objects, by planets and stars, which we still do not understand. And an interesting thing about cosmic magnetism is, not sure if any of you have ever experienced the Northern Lights, the Aurora Borealis. But so just to tell you, it's incredibly underwhelming. I was in Iceland a couple of weeks ago, and you see these beautiful images of the aurora, all this green and blue and purple, and you go there and you're hoping to see that. But all you see are just like white clouds basically moving around. But at the same time, through the camera, you would be able to see exactly what you see. It's just that at night, your eyes go into low light mode. You're unable to pick up the same light that is actually there. So say if you sit around for maybe 5 to 6 hours in the dark, you will start to see that. But now that is caused by cosmic magnetism. So solar flares from the sun, when they react with the Earth's magnetic field, is what causes phenomena such as the aurora borealis. Another thing that needs to be investigated is something called dark energy. So as mentioned, our galaxy is expanding. The universe is drifting further and further apart. And scientists initially thought it would be the opposite. They thought that the gravitational pull of the galaxies would be bringing the Earth together. But they recently discovered something called dark energy. And a Nobel Prize was won for the discovery of dark energy a few years ago. And so it's still a lot is not understood about dark energy, mostly because existing radio telescopes are not able to see that far into the past. And that's the amazing thing about radio telescopes, is that they initially look into the past. We see things that happened millions of years ago. We see how things were created. This is the example of how the universe is expanding. So with a stationary galaxy, the radio waves, as they would reach the telescope, would be exactly identical from the start to end. And with the galaxies moving away, we start noticing that the radio waves are being stretched. So back to, so this part regarding the aliens again, because a lot of people always think that we're trying to detect extraterrestrial life. And I don't blame them for thinking that, because when these kind of projects are always initiated and people are told about them, people want to know more about it, because people aren't interested in galaxies, in dark energy, how stars are formed. People are interested in aliens and extraterrestrial life. So projects like this can help investigate that, but not in the sense of finding little green men. That's not what's being done. When thinking of extraterrestrial life, it's more in trying to find planets in solar systems similar to ours, so-called the Goldilocks zone, which represents planets that are inhabitable, planets that have similar atmospheres, similar terrain to Earth. So we can use radio telescopes to detect like cosmic or organic molecules that are the building blocks of life. Astrobiologists, for example, can detect the spectral frequencies of amino acids, which would indicate the presence of life. And it can also be used to detect extremely weak signals emanating from distant planets, which could potentially prove that there is potential life out there. Once again, life could be anything ranging from microorganisms to bacteria and not necessarily aliens. Okay, so when are they doing it? Now, this is probably not of interest to anyone who's not a project manager, but this project was started way before 2005. So 2013 is when it started getting into the initiation and the building phase. So at the moment, we're still on track. Around about 2017, 2018 is where the construction has been approved for SKA phase one. I'll get into this a bit later, but the project is going to be built in different phases. It's a very long-term project going up to the mid-2020s. So where are they going to be doing this? So initially, when this project was started, there was a request by the SKA steering committee for different countries to make proposals on wanting to host this, similar to an Olympic bid or a World Cup bid. And there were multiple proposals from 5 countries. It was the USA, Argentina, South Africa, Australia, and China. Those were the initial 5 hosts. The USA then pulled their request. I think there was maybe no funding available. I think it was around the same time that they were cutting down on their space funding. So they decided to pull out of this. I think they wanted Mexico to build it for them, but they also refused. So in the end, it was decided that it would be between South Africa and Australia, and those were the 2 bidders in the long run. And it's interesting that South Africa and Australia were chosen, and also that Argentina was a forerunner. And that's mainly because they're in the southern hemisphere. And in the southern hemisphere, you generally have a better view of the sky and better. So these are 2 words that I need to look at because I keep forgetting them. 2 keywords, jargon here, that I had to Google. They have ionospheric stability and benign tropospheric conditions. So now, I don't know what that means either, so I'm just going to read it. So ionospheric stability is the ionosphere is basically it's the area of the atmosphere where it's ionized by solar and cosmic radiation. So now you need that to be very stable because that radiation can affect the radio signals. It can deflect them, it can cause them to scintillate, and then you wouldn't receive the signal that you're interested in. So fortunately, in the southern hemisphere, we don't have much of that. So the radio waves can pass through unfazed by it. And then regarding the benign stratospheric conditions, so that's the lowest layer of the Earth's atmosphere. It's basically where all the weather happens on Earth. So in the southern hemisphere, we don't have many hurricanes, tornadoes, and the sort of things that you would experience in, I think there's a lot of that here in California specifically. Am I right? No? Yes? Maybe? So we don't have much of that would affect the radio waves, which is why the southern hemisphere also has one of the best views of the Milky Way. And that's why, in the end, it's going to be a bid between South Africa and Australia. Each of them had to build their precursors or their pathfinders to prove that they have the capabilities. And we'll get into that just now. So in South Africa, the area where it's being hosted is in the middle of the Karoo Desert. And that's how it currently looks like. These are real images that the current, this is actually from a couple of years ago. So a lot of these pedestals have been filled now with further telescopes. And in Western Australia, it's being built in the Murchison Shire. And it's also very similar terrain. Once again, these are real images, very similar terrain. Once again, very arid terrain, very densely populated. Usually, if there are any people living within these areas, their land is bought out and they are made to move. A lot of people aren't happy about that. And there's also no radio interference in any of these places. So there are no cell phone towers, no radio towers. So it's completely radio silent. So this is SKA phase 1. Like I said, SKA is going to be built in 2 phases. SKA phase 1 is going to be built until around 2020. And afterwards, SKA phase 2 is going to add on to that. This is just how SKA phase 1, which is already about halfway through, compares with some of the world's largest telescopes at the moment. So SKA is going to be comprised of the low frequencies and then the mid and the high frequencies. So the low frequencies are going to be built in Australia, with the mid and the high frequencies in South Africa. The low frequencies will comprise of approximately 130,000 antennas with a total collecting area of 419,000 meters squared. And now compared to the current world's largest, which is the LOFAR in the Netherlands, which is only 34,000 antennas and 52,000 meters squared. With SKA mid, that's going to be in total approximately 200 dishes, including the 64 meerkat dishes, and 33,000 meters squared. which compared to the very large array in the USA at the moment, which is the current largest at 13,200 meters squared and 27 dishes. And also, just to note that the SKA, unlike some of these other dishes, is going to be completely steerable. So it's completely adjustable. Some more information here about the SKA phases. So phase 1, once again in South Africa, 33,000 meters squared. In case you can't imagine that, is 126 tennis courts. So it's always easier to imagine things in tennis courts. A maximum distance between the dishes, which is known as the baseline, is going to be 150 kilometers. And one of the biggest issues that we are going to have with the SKA is the concept of big data, considering the amount of data that is being output by these telescopes, 2 terabytes per second, approximately. It will probably be more. These are all just estimations. So there's recently been assigned an agreement with CERN at the Large Hadron Collider to share with their big data initiatives in order to process this kind of information. And then phase 1 in Australia, once again, much smaller collecting area, lower frequencies, and I'll show you some images of what that looks like at the moment. So what's been done so far? So as I mentioned, prior to the sites being selected, each country had to build their own telescopes to prove that they have the capability to do this. So in Australia, there's the Australian SKA Pathfinder and the Murchison Wide Field Array, whereas in South Africa, there's Meerkat and Hera, which is the hydrogen epoch of reionization. So this is ASCAP at the moment. Meerkat in South Africa. This is one of my favorites because it looks like futuristic sci-fi spider drones. And it's not just this one set. There's about hundreds of these. I just chose this image because of the beautiful backdrop. And this is Hera, which just looks like upside down umbrellas. Okay, so back to me again, Omer Mahgoub. And just like to mention at this point that I had actually always wanted to be an astronomer. Not because I'm fascinated by the galaxy and the universe and all of that. I mean, that's amazing, sure. But I wanted to be an astronomer just so that I could tell people that you can't spell astronomer without Omer. So I'm currently working at SKA Africa on the Meerkat project for the digital backend team, and I'll get into a bit more detail about that. So that's where Cape Town is on the map. I don't know if any of you have ever been there. No one? Yes? You should definitely go. It's a beautiful city. It's I've been told it's very similar to California, to San Diego, and I've noticed that it's a very relaxed beach city. So that was a stadium built for the World Cup in 2010. The back at the famous Table Mountain. Probably not that famous if you guys haven't heard of it. And it's also the southernmost tip of Africa, so you could actually go to the point where the Indian and the Atlantic Oceans meet. So the digital back end. So before I get into the digital back end, I'd like to tell you about the telescope front end. So the front end of the telescope is used to pre-amplify radio waves, and it also extracts the signal from the required frequency bands that you would like. So we don't work on that. That is done by a different department. We focus more on the digital back end. Once again, that's a zoomed-in image of the telescope front end. Now, the telescope back end, that's what's responsible for all the digital conversion, manipulation, and storage of the sky data that you receive. All the analog signals are basically digitized, manipulated, and stored. And that's all with these processing boards, and this is where Altium will come in. I just feel like I have to say a lot of good stuff about Altium or I'll get kicked out of here, and that will be coming. So, Meerkat. So initially, there was CAT, which is the Karoo Array Telescope, and this consisted of 7 dishes, each about 12 meters wide. And it was decided that we would want to increase CAT. We wanted to make CAT bigger, essentially. And so Meer is an Afrikaans word. Afrikaans is one of the 11 languages in South Africa. Meer means more. So it was decided that we would have more of CAT and call it Meerkat. Okay? But also, that's not all. But also, a meerkat is this. I don't know if you've ever seen these creatures. They used to have their own show on Animal Planet called Meerkat Manor. So this is also a meerkat, and the area where the telescope is being built it's run wild with these creatures. So meerkats. So I just have a little video here to play for you about meerkat, because 45 minutes is a long time and I need to fill a few minutes. So, so just some information about the meerkat antenna. So you might have heard me also use the term dish. They use dish, receiver, antenna, but our mechanical team gets really uptight about people calling these dishes. They'll tell you that dishes are what you eat on. These are receivers or antennas, not dishes. So it has a total height of 19.5 meters, and it weighs approximately 42 tons. Just a human there for scale. And so it has the main reflector over here, and then it has a sub-reflector, the smaller sub-reflector, which is about 3.8 meters. And then at the front, you have the indexer. And what the indexer houses are the receivers for the different frequencies. So there's the L-band receiver, the X-band receiver, and the UHF band receiver, each operating at a different frequency. And as well as the receivers, it also has the digitizers for each of those frequencies. And then over there, below the pedestal, you have the underground network of cables that transmit the data. It's roughly 15 kilometers to the processing building, all fiber optic data. And then the pedestal also contains all the bearings that allow you to move the dish in either direction. So these are just some of the images observed by meerkat over the years. So what we see here is actually we're looking at a black hole, and what you see are the particles being ejected by the black hole. So over here, Cat7 in 2012, it was essentially just a blur. Then Meerkat with 4 dishes in 2016, slightly improved, but still just a blur. And then eventually, in 2016, with Meerkat and the 16-dish configuration, you could more clearly see what was happening with the black hole and the ejections. And then the same Meerkat 16 once again, maybe using software version 18.0, slightly clearer once again. But what I find amazing about this is that back in 2012, when these images of Cat7 were released, people were still in awe. They were like, oh my God, this is so amazing. Look at this incredible imagery. And it's only now when they look back and they realize how horrible it was actually was at the time. It reminds me of when I was a kid playing on maybe like a Sega 16-bit, playing FIFA 95 and thinking, these graphics are impressive. We will never get better than this. It's like the peak of humanity. You know, that's how people felt initially with Cat. Some more images here with Meerkat. And so this over here, it's a deep field space. It's called, I'll have to check the name again, but it's an area in the Milky Way. I'll just call the small area in the Milky Way. And it's being observed, it's a comparison between Meerkat, and those are the best images ever observed of that section using the ATCA telescope in Australia. So as you can see with Meerkat, with the slightly increased sensitivity, you are getting a bit more detail and more resolution, and certain images, certain parts of it that weren't visible before are becoming visible here. Over here, this is the image of, it's called the Deep 2 field in space. And this was actually the first radio image ever imagined of this. So that's the optical wavelength on the left. This was taken in the 70s. And since then, we haven't been able to obtain a radio image of that space until Meerkat came about. And once again, you can see it's very similar. These waves were sent approximately 250 million light years ago, the images that we're looking at. So more about the Meerkat receiver. Just once again, for scale, we have the receivers for the different frequency bands, the digitizers, and the human being for scale. And so the Meerkat digitizer, that's the most essential part of the Meerkat processing system. And basically what it consists of is you have two polarizations, a horizontal and a vertical polarization. So this is basically the antenna data that's being received. This is passed through an RF conditioning unit, the output of which is then transmitted to an analog to digital converter. From there, it's passed onto the D engine, which is used to digitize and process the signals before it's further outputted to our fiber optic connectors. But I'll get into more detail about these different subsystems as we continue. So the digitizer looks like this. This is our current digitizer. And the reason that it looks like this is for two reasons. Mainly, the fins is heat sinking, because as you might recall, this is in the desert where the temperatures fluctuate from -15 to 50 degrees. So you need incredible amount of heat sinking, and also considering the amount of heat generated by the components inside the digitizer. And another reason that it's built this way is also to prevent any EMI, any radiation from within the component that might affect the signals that we are trying to observe. Once again, these are the six systems inside, as mentioned. So we have the RFCUs in the middle, the RF conditioning units, then the two ADCs below that, sample clock generators, and then the D engine right at the top, which is the digitizer processing board. So we have different frequencies. We have the L band, UHF, and the X band. I can just get back to here. So the X band is between 8 to 14.5 gigahertz. The L band is between 0.9 to 1.67 gigahertz, and UHF is between 0.5 to 1. No, sorry, these are the frequencies. Oh, sorry, we're digitizing at 1712 megahertz. 1712. Sorry, those were just the frequencies of interest. So I think we'll get to that just now. And then these are the fiber optic connectors. Once again, we use military spec connectors because there's a lot of dust and sand where this is being built. So we need to ensure that none of that gets in here. So the RF conditioning unit, this is what receives the signal from the receivers. It just amplifies it to the correct signal levels required by the analog to digital converter, and it just performs a little bit of filtering on the incoming signals. And this is what our RFCU looks like, proudly designed in Altium. Then we have our sample clock generator. So one of the most important things for a radio telescope is timing, because we're essentially getting the different timing from different telescopes. So for that purpose, we actually use a hydrogen maser because it's one of the most accurate ways to time. The sample clock generator, this generates the clock required by the different ADCs, as well as the high precision synchronization pulse between the different digitizers on the system. So at the back is essentially just your power coming in, and then the different modules at the front. So this is the sampler, our ADC. It's a 10-bit ADC at a rate of 1,1712 megabits per second. Then we have the backplane. So the backplane is at the back of that box that I had showed you previously, and that is where all these modules plug in to get their power. So it essentially just has filtered D-sub connectors providing power to all the components. And then the D engine, which is essentially the heart of the digitizer. It packetizes the raw ADC data. So the ADC data is received via these two fiber optic connectors. It passes through a set of CML to LVDS converters. It goes on into two demuxes that you would see on the left and right. So it's demuxed by 4, and then it's passed onto the FPGA where it's processed, and then it's transmitted via fiber optic interfaces. to our processing building. And all the components that are in the digitizer are also shielded. Each one is shielded on their own, once again, to prevent any EMI radiation. This is just the D engines being tested. Probably looks much better in Altium 18. So the D engine, it's a 12-layer board, and it consists basically of the 2 fiber optic receivers, 2 D multiplexers, and 1 FPGA. It's the Xilinx Kintex 7 FPGA. It is a 12-layer board. We're alternating signal and ground planes. Of course, because of the high-speed signals, we need to have them pretty well shielded. So we have basically a mixture of mixed coppers in this board as well, 35 micron coppers and 70 micron coppers. And just, okay, I think it's still coming. There's another board where I'll get into more detail with the stack up of this board. And then so this is essentially, I mean, this could probably have been done better looking back at it now. But these are essentially all our length-tuned differential pairs between the demultiplexers and the FPGAs. So these all need to be extremely accurate. They all need to be, I mean, you can make up for it with the FPGA, but you'd rather have your hardware done correctly rather than optimize for it in firmware. So these are all our signals, match length to within, it's probably a bit of overkill, but we try to match length within a couple of millimeters. Once again, same, these tracks are all, they're about, I think at the time it was formal and formal track and gap. So one of my favorite things to do in Altium is pin swapping, because that comes in incredibly useful for these large FPGA designs, especially when you have your multiple GPIOs. So that just makes things incredibly easy for us. So now that we've spoken about the digitizer, you're probably wondering what happens after the digitizer. What happens next? So after the digitizer, after the D engine has transmitted the signal, it's all transmitted via fiber optic cables to the KABP, which is the Karoo Array Processor Building, which is an underground bunker where the signals undergo the digital signal processing and storage. So there are two main processing techniques that occur: correlation, which combines all the signals from all the receivers to form an image of the sky that is being surveyed. It basically creates one image of what's being received by all the telescopes. And then beamforming, which forms a narrow, high-sensitive beam from the received signals. And that's what allows it to operate as one dish instead of as an array. So this is the KABP, and it's about 10 meters, around 10 meters underground. And it has approximately, I think it's kept at about under 5 degrees. And it's basically power on the one side and processing on the other side. And then we get to Roach. So Roach is our reconfigurable open architecture computing hardware. Now these are basically the heart of the digitizers in that they do all the processing. So initially we had Roach 1, which basically consisted of, this was done in the early 2010s, so it was a Vertex 5 FPGA with a Power PC to provide control functions. It had 4 10 gig high-speed connectors, CX4, and it had just very little memory, some QDRs, a DDR, and a ZDock connector for the differential pair outputs, as well as some USB MMC slot and some Ethernet connectivity. So I'm not going to speak too much about Roach, because Roach was not done in Altium. So we won't focus too much on Roach, but this was essentially Roach. And now Roach is still being used. It's being used a lot by the team at the University of California in Berkeley that are using Roach. I don't know if you guys are familiar with SETI, Search for Extraterrestrial Intelligence. SETI are using a lot of the Roach boards as well. That was the highlight of Roach, our heat sink with the blue lights. This is Roach with just with an ADC card connected. And then after that, we updated it to Roach 2. So naturally, we had to progress. It was to a Vertex 6 FPGA. We still kept the PowerPC. We had two multi-gigabit transceiver slots supporting CX4 or SFP up to 8 times 10 gigabits. We had four 36-bit SRAMs. We had a single 72-bit DDR3 RAM, two ZDoC interfaces for the ADC and the DAC, and also we had a USB to JTAG, serial, and I2C connectivity. So here's Roach 2. So at the bottom is your ZDoC connectors. At the top, your SX4 connectors. Then we have this FPGA, the PowerPC, and all the supporting memory. So Roach 2 was also a 12-layer board. And no, actually, this was a 16-layer board. This was a 16-layer board that we had done. Once again, we had the same struggle. We didn't have active router at the time. So all of that had to be manually routed, manually matched length, manually tuned. So it was very time consuming. So I had joined SKA just after Roach 2 had been designed. So I had just worked on a few updates to Roach 2, but I hadn't done the bulk of it. Like once again, this could probably have been done much better. And now we've moved on from Roach to Roach 3, but we've decided to change the name. So we've gone from Roach, and sticking with the insect life, we've changed it to Scarab. What Scarab stands for is the SKA Reconfigurable Architecture Board. And the reason that the name was changed was that Roach was initially being just used for Meerkat, and at the time it wasn't known whether Meerkat would be a part of SKA or not. But now, after Meerkat had been absorbed to become part of phase 1 of SKA, it was decided that future boards would incorporate the name SKA in it. So Scarab, once again, they've messed up my. So Scarab, once again, it features a Vertex 7 FPGA. Once again, we've moved up 4 megaray transceiver slots, QSFP mezzanine cards. Then we have optional HMC mezzanine cards, which I'd like to get into some detail about. If we have time, 1 gigabit Ethernet, and some more memory. And so these are how the Scarabs are. We have racks of Scarabs, 1 new racks of Scarabs in the processor building that do all our computation. These are the QSFP mezzanine cards used on Scarab, the ADC mezzanine cards used on Scarab. So these are all optional. These aren't required. The Scarab was built by a third party, and it's also being sold to other companies for their own purposes. So for SKA, we do not use the ADC and the QSFPs of Scarab. What we do use is the hybrid memory cube mezzanine card. I'm not sure if anyone here is familiar with HMC, hybrid memory cube, or have used high bandwidth memory before. But the hybrid memory cube, it was used for data storage. It consists of 4 gig serial memory using 16 10 gig SerDes lines. So the structure of a hybrid memory cube is that you have your silicon substrate, and then you have stacked DRAM layers on top of the logic layers. So this was an innovative new memory scheme instead of DDR. And at the time, DDR3 was not sufficient for our use, and so we decided to use this hybrid memory cube, although it was still at the experimental stages. This was being designed by Micron. So we had built our first HMC board. It was a 4-link, so that's a 1 millimeter BGA, 996 pins. And we were happy to go forward with this until we were contacted by Micron and told that they would not be producing these chips. The reason they would not be producing them is that they were having problems with thermal escape due to the stacked layers of these chips. So they decided they would not be producing this, and we had to redesign for a 2-link HMC board. And now this was much more technically challenging because instead of the 1 millimeter pitch, it was a 0.65 millimeter pitch BGA. So we needed to incorporate incredibly narrow traces up to 3 mil. And at the time, manufacturing of PCBs in South Africa did not cater for this kind of technology. We did not have the means to be able to produce this. And we also had to use blind microvias to reduce the stubs for the data transmission. So this was the redesigned HMC board. And funny enough, after we had designed this, Micron once again got back to us, and they said they would be discontinuing this chip as well. But fortunately for us, we bought all the remaining stock. And afterwards, they've moved on now from the 2-link. They've moved back to the 4-link 2 gig device, which is what they're going to be mass producing. But we've got all the chips we need for now. So the HMC basically just consists of the memory cube in the middle, power supplies on the left, and some supporting circuitry here on the right, with the mega ray connector at the bottom. No, no, we're gonna. This is just the HMC in its heat sink, because once again, it's the memory chip really has a lot of trouble getting the heat out, so we needed a lot of heat sinking involved. So no, there's not much more. I think it's mostly from here. It's just the layouts of the HMC. This was the layer stack that we used, and what we needed to incorporate because of the HMC, there's a lot of different power rails of the HMC, up to 7 power rails, and there was not enough space on the board to incorporate all our capacitors, all our decoupling caps for those, which is why we had to use buried capacitance cores on this board. Some of the routing on the HMC. These are the blind wires that we use to reduce the transmission stop, because this is operating at 15 gigs per second. So we had to try to get it to be, the signal integrity to be as good as possible. And then this is just the fan out that we use for the BGA. And the decoupling, we had to incorporate 0201 capacitors. I think you guys call them 01 or 05 or something over here. But 0201 capacitors had to be incorporated for decoupling. So this was one of the features that I enjoyed using in Altium during this. It's the removing unused pad feature. This came about, I think, in Altium 2015. But we'd have areas of really narrow copper on your BGA planes during your fan out. And so then the copper width is way too narrow. So what you do is you have to first select the area in the BGA that you want to alter. You go to your tools, remove unused pad shapes, and it automatically makes it much larger. So this, I had no idea about this until I was told by one of the application engineers at Altium, and it was a very useful feature at the time. So this is my last slide. This is probably not going to be the same without sound, but this is just a recap of SKA. Probably good that there's no sound, since I had no rights to the music. It's usually much faster. Okay, thank you.
Thanks, Omer.